Hey guys, welcome back to a new unit on quadratics. We're going to be looking at all things that deal with parabolas, quadratic equations, basically equations that have a highest exponent of 2, and some features that go along with these different types of graphs, such as roots, zeros, and solutions. That's what we're going to start off with today, and looking at some graphs. I have a couple of different examples of graphs of quadratic equations, meaning that they have a parabola, right? It's a U shape, either a U-shaped up or facing down. Okay. And a couple of examples of what these graphs might look like and how they're different and, for that reason, important. For example, what you might notice about these first couple of examples is that the parabolas touch or kiss the x-axis one time. Whereas for our second examples, whether they face up or they face down, in both of these examples, the graphs intercept the x-axis twice. And in these last examples, never touch the x-axis at all. Now that's going to be important to start our unit because that's going to describe the number and the type of solutions, roots, or zeros that you'll have for the specific equation that corresponds or matches each of these graphs. So in Algebra 1, you probably remember that when something touches the graph once, that means it has one solution. Or when it intercepts the x-axis twice, it has two solutions. And back in Algebra 1, you might have been told that if it does not intercept the x-axis, it has no solutions. We're going to tweak that a little bit, make it more refined and corrected based on what we learned in our last unit about complex numbers. So, revisiting these graphs, what we can say is that if a graph touches the x-axis once, it has one real solution. Okay? It's important to say that this is a real solution. It's a number that you can find on a number line, right? We talked about how there's a difference between real numbers and complex numbers. Okay, that's going to resurface here in the context of these graphs. If a graph touches the x-axis once, there is one real solution. If the graph intercepts the x-axis twice, okay, in that case there's going to be two, again, real solutions. It hits it twice, right? This is a quadratic graph. There's going to be multiple solutions possible for some of our different equations. And in this case, you can have two different solutions to the same equation. So we'll see an example of this shortly, but for a graph that you're looking at, visually speaking, if you see that it intercepts the x-axis twice, it has two real solutions. Now, what about the graphs down here, right, where they don't intercept the x-axis at all? Are there no solutions? Well, there's no real solutions, but actually, now that we've learned about a new type of number, there are solutions, roots, or zeros. In fact, there are two complex roots, solutions, or zeros. Even when it does not touch the x-axis, there's still an equation that matches these graphs, and that equation can still be solved. It can't be solved with real numbers. So back in Algebra 1, you weren't aware of complex numbers, but now you are aware of those numbers, and so some graphs that you see will have solutions, and in this case, you'll have to use the equation to help you figure out what those solutions are. They will be imaginary or complex. So this is important. Notice that you cannot have one complex solution to a problem. There's a reason for this. We're going to get to that shortly, but remember this is impossible. Okay? Complex solutions always come in what's called conjugate pairs. Pairs means two. So let's take a look now, instead of some graphs, let's take a look at some equations that you could graph if you wanted to. And I will recommend that you try to graph these equations just to confirm that the solutions we get make visual sense according to what we have seen about our graphs down here. So I'll explain that in a little bit. But if we are given just a function or an equation, remember all of these things can match a certain graph, right? So the steps to solving algebraically, looking for solutions, roots, or zeros just from an equation, not from a graph, are listed here, but they should match the graph that goes with this equation. So when you graph this, and you look at the solutions, roots, or zeros that it has, whether they're one real solution, two real solutions, or two complex solutions, whatever we find here, had better match the graph that we have down here. So let's follow these steps, see what solutions we find specifically, okay? And then see if the graph matches those solutions. So when we're solving using the root method, there's a couple different ways that you can solve these problems that we'll see in this unit. You have completing the square formula, you have the quadratic formula, you have factoring. We'll get to those in different videos. We're going to start with the root method of solving different problems. And the first step is going to set our function equal to 0. Okay. We want to see what happens around the x-axis, right? What happens when y is 0. Okay. So rewriting our problem, our goal is going to be to isolate x, right? Solve for x. And the way that we do that, I like to put a box around my variable, right, my x that I'm looking for, and leave it on one side of my equation and move everything else to the other side by opposite operations. So, for example, the opposite of a subtraction problem is addition. So we're going to add 121 to both sides. This way, right, we can cancel out something on the right-hand side. X is a little bit more isolated now. And on the left, we have to do the same thing to balance the right side. If we add to one side, you have to add to the other. Okay. So now what you have is this. Okay. Notice I have a 16, that's my coefficient. I want to also get rid of that. Remember, my box needs to end up by itself. So opposite of multiplying by 16, divide by 16 to both sides. Okay. So right now we have x squared equals 121 divided by 16. Now you can't reduce this, right? It's a fraction, non-reducible. So what else can we do here? Well, notice I've put a box around x, but not that 2, right? That exponent is not a part of my variable, okay? We can get rid of that exponent by opposite operations as well. The opposite of a square is going to be a square root. So we need to square root both sides. Just like the opposite of addition is subtraction, multiplying is dividing, opposite of a square is a square root. So if we square root both sides, now x is going to end up by itself. Okay. Importantly though, it's important to remember that when we take the square root of both sides of a problem, we always need to have a little plus and minus symbol in front. So this should be plus and minus. The square root of 121 is 11. The square root of 16 is 4. Our answer should be plus and minus 4. Now why is this? Why does that plus and minus symbol show up? Well, here's an example that might be a bit easier to understand. Okay, what times what equals 4? Now some of you might say 2 times 2 equals 4, and that is half right, but remember, a negative times a negative also equals a positive. Negative 2 times negative 2 also equals positive 4. So x needs to be plus and minus 2. Or if you want to split them up, this is another way that you could write your answer. Okay, whoops. One of them negative, one of them positive. Okay. X can equal negative 2 or positive 2, plus and minus 2. That's a shorthand way to say that we have 2 real solutions. Same thing down here. We have 2 real solutions, not just 1, 2. So how would that look like on a graph? Well, if you go back and try to type this into the calculator, okay, the graph will look something like this. And notice, we have 2 real roots, right? 2 places where the graph intercepts the x-axis, and specifically at plus 11 over 4, minus 11 over 4. That's very close to plus 3 and minus 3, but since that's not a 12, it doesn't simplify. This would be the 2 specific real roots, zeros, or solutions to our equation or function, and that's matched by the graph of this equation or function. So everything matches 2 real solutions from our graph, 2 real solutions more specific from our actual function itself. And that's how you double check yourself. Always graph your problems to make sure that whatever you get after solving visually matches what you know that they should be. Okay. So one more example. And in this case, I'm going to show you what happens when we get complex solutions. So again, goal going to be to get x by itself. And by the way, this y is just the same thing as f of x, if you didn't remember that. F of x and y mean the same thing. We want to set both of those equal to 0, again, because we are interested in what happens around the x-axis, right? So, x, get that by itself. The way that we do that, subtract 81 to both sides. I guess I'll rewrite the problem first. So x squared plus 81, we've changed that y to 0. Subtract 81 to both sides, opposite operations. Okay. Remember, the opposite of a square is a square root, so we're going to square root both sides to get x by itself. But when we do that, always remember a plus and minus symbol should show up in front of the square root on the other side, right? Just like we said before, positive 2 and negative 2 are both solutions to the other side. Same thing here. Positive square root of negative 81, negative square root of negative 81. Okay. Those are two solutions that we're going to find, not just one. So, okay, well, how do we simplify the square root of negative 81? We saw this in the last unit, right? We know what the square root of 81 is. Square root of 81 is just 9. 9 times 9 is 81. But the square root of negative 81, okay, that's going to be 9i. Aha, imaginary numbers, complex numbers, right? This is really the same thing as the square root of 81 times the square root of negative 1. And this is 9, and this is I, and multiply those two together to get 9i. Okay, so what that means is we have two complex solutions as our answers, plus and minus 9i. Okay, plus and minus 9i. And hopefully this answers the question that we saw earlier, right? Earlier I had mentioned it's impossible to have one complex solution as our answer. Why? Because this plus and minus symbol always means that there's going to be two answers to our problem. The only time that won't be true is if we have something like x squared equals 0. Okay. If I have x squared equals 0, yes, square root both sides, yes, plus and minus symbol shows up, but the square root of 0 just is 0, and there's plus and minus 0, they mean the same thing, right? In this case, x equals 0 is a repeated solution. Okay. That's the type of problem or graph where it'll kiss the x-axis once at 0, 0. So that's a different type of problem. Here, though, we can see clearly that we have two complex solutions. And the graph of this, by the way, if you went ahead and graphed this using, and I'm going to mention this, desmos.com / I believe it's calculator. Type that in, go to that website, and if you type this function in, or this equation into your graphing calculator, what you'll see is that the graph looks something like this if you zoom out. It's a parabola that never touches the x-axis, which makes sense because, as we've said before, we have two complex solutions, not two real solutions. They shouldn't touch the x-axis if our solutions are imaginary or complex. So that's a brief intro to the new unit on quadratics. Main points here. Okay. Remember, quadratics always deals with parabolas. There's different types of parabolas. Whether they touch the x-axis or not are important. If they touch the x-axis once, one real solution. Twice, two real solutions. No times, two complex solutions. There's no such thing as one complex solution. And then just be able to use opposite operations to isolate x on one side of your equation, solve, and then compare. Does the answer that you get make sense when you compare it to the graph of the original problems? They should. The answer should make sense. The same number and type of solutions that you get here should match the graph. So hopefully that